Welcome back to a new video. Here we go, the insane engineering of the F-35B. Check out the original video in the description as always, and comment below what your thoughts are, what you want to see next. But let's get into it.
I've never flown an aeroplane like this where you can control the motion of the aeroplane so precisely.
I'm not sure we've even scratched the surface yet of what this airplane, when it's operating with other F-35s, is going to be able to do.
The F-35B is arguably the most advanced plane ever made. A jack of all trades, a stealth fighter plane, combining and improving on the capabilities of the F-16, AV-8B Harrier and the B-2. A highly maneuverable fighter plane, capable of attacking both airborne and ground-based targets. A stealth fighter taking the lessons learned from Lockheed's previous ventures into stealth with the F-22 Raptor and the F-117 Nighthawk. A plane fitted with the most advanced sensors and computer systems, sharing information almost instantly with allies without compromising stealth, and presenting the information directly on a heads-up display on the pilot's helmet visor, giving unparalleled situational awareness, allowing a flight of F-35s to effectively fight as a hive mind. Perhaps most boldly of all, the F-35B is capable of transitioning from horizontal to vertical flight with a push of a button, using directional thrust and a massive vertical turbofan engine hidden within the plane's body, making it possible to land like a helicopter on the relatively small amphibious assault ships of the US Marines. This is the insane engineering of the F-35B. Fitting all these capabilities into a single airframe is an extremely difficult task. Designing for stealth demands careful molding of the exterior of the plane, dictating the design of crucial features, creating unavoidable trade-offs. There are a lot of misconceptions about stealth. The goal isn't to make the aircraft invisible. It will be detectable. The goal is to delay enemy detection for as long as possible. For bomber aircraft.
See, that's a great point. Apart from this looking absolutely insane, it just looks like an incredible aircraft. The capabilities of it, what they've already said, which they go into more detail. You know, yes, it's a fighter jet. Yes, it can attack airborne and ground targets. It can dogfight, but it can also carry out surveillance and reconnaissance missions. And he's just put it there. It's not about, an aircraft isn't going to be completely invisible. It's just not possible, especially with today's technology. But as they go into it, it's about getting as close to the enemy as possible without getting detected, so you can either attack or gather as much information as possible. And then at some point you will get detected, and then that's when you're going to have to move away. And it's delaying that so you can get as close as you possibly can to gather the best intelligence or have a higher chance of hitting that target.
Aircraft, it shrinks the range of the enemy's radar stations, potentially opening gaps in radar defenses and allowing the aircraft to slip through undetected. For fighter aircraft, it provides a critical advantage: detect your enemy before they detect you. To gain these advantages, we need to make it harder for the radar receiver to decipher whether the return signal is just background noise or an enemy aircraft. To do that, we need to minimize the strength of the return signal. There are several mechanisms for a radar wave to be reflected. The most significant and most obvious way is through spectral return, otherwise known as regular reflection, like a mirror, where the angle of reflection equals the angle of incidence. We want to avoid large, flat surfaces that could reflect straight back to the radar receiver. Corner reflectors where two surfaces are set at a 90-degree angle to each other need to be avoided at all costs. Tailplanes consisting of the vertical and horizontal stabilizer are the perfect surfaces to create a corner reflector, allowing radar to bounce off both surfaces and return right back in the direction it came. The best way to avoid this is to remove the tail completely, like the B-2, but this impacts maneuverability greatly. Instead, we can replace both the horizontal and vertical stabilizer with a V-tail, as seen on the F-117 Nighthawk. The V-tail can act as both a rudder and an elevator, and we can see how by examining the resultant force generated when the control surfaces are actuated to different positions. We can actuate them in opposite directions to generate a horizontal resultant force, providing yaw control as a vertical rudder would. or we can deflect them in the same direction to provide pitch control as a horizontal elevator would. This configuration is sometimes used for unique looking aircraft like the Cirrus SF-50, allowing it to mount a single tiny jet engine on top of the fuselage, with its exhaust directed straight through the V-tail. A private jet so tiny and lightweight that it can deploy a parachute to rescue itself in emergencies. Having rudder and elevator controls linked to a single mechanism like this is not ideal. Fighter jets like the F-35 and the F-22 need superior control authority, and that is a function of control surface area. The larger the elevator, the larger the pitch control. If a control surface is working a double role, where rudder and elevator action is needed at the same time, it reduces the control authority. So, both planes also feature large elevators, offset by a distance and angled to prevent corner reflections.
It's very smart and very technical, and it's a lot of information to take in. For those of us that aren't geeks and boffins and got brains that big, it is very, very technical, but I totally understand and get what they're saying. So obviously it's our technology really advanced, and it's amazing to see how far we've come on. But basically, yeah, they've got rid of that right angle, they've got rid of any flat surfaces, which is then going to stop that detection. So in the most basic simple terms, and I think it's amazing how they've managed to do that but still keep the maneuverability and the agileness for it to be a top fighter. Absolutely brilliant.
We can see many more trade-offs in design by comparing the F-117 and the F-35 in the quest to fulfill both stealth and fighter requirements. Both the F-117 and B-2 have their engine air intakes mounted on the upper surface of the plane, which prevents ground-based radar from bouncing around inside the intake and back to the receiver, and helps reduce infrared heat signatures. However, for a plane expected to make high angle of attack maneuvers in life and death situations, this isn't a design you would want to include. While performing a maneuver like this, the air intake will receive lower pressure air, which will lower performance right when performance is needed most. Air intakes located underneath the aircraft, like the F-16, will cause too much radar return. So, twin intakes located on either side of the fuselage are instead chosen. These air intakes have some clever aerodynamic features too. This seemingly innocuous bump plays an important role. This is aeronautical engineering epitomized. Every seemingly insignificant design feature has a purpose. Mounting engine intakes along the body of an aircraft comes with some issues that pylon-mounted engines avoid. As air travels along the length of the body, air begins to form a layer of slow-moving, turbulent air called a boundary layer. If this air is allowed to enter the engine, it not only lowers performance, but it can also damage the engine. As the turbine rotates, it will pass through the slow boundary air on one side and then fast stream free air on the other. This means the force on the turbine blade changes for each and every rotation, causing cyclical bending, a recipe for fatigue failure. Planes like the F-16 feature a boundary layer diverter that separates the inlet from the fuselage with a small gap. But this design increases radar cross-section and increases drag. Later variants of the F-16 tested the DSI, the divertless supersonic inlet, essentially a large bump that creates a region of compression that pushes the boundary layer air away from the inlet, while also scattering incoming radar and lowering drag. The test flight demonstrated that it could meet performance requirements, ushering in its introduction to the F-35. The final product reduces weight by 30% and lowers production and maintenance costs. Moving down the plane, we can...
So basically there's a layer of slow air going over the aircraft, and we want to prevent that from entering the air intake. What I don't get is, I would like to know, understand a little bit more, is obviously they're mounted on the side, and it is very technical, how the air obviously brushes around so the boundary layer doesn't go in. How does, because the air intake isn't on top, how does that prevent the radar from bouncing around on the inside? It's very, very technical. I wish I was a lot smarter, but absolutely insane engineering. and absolutely astonishing, and it's so great to see how far technology has come and that this is capable of being built.
See other hints of stealth design. Long sharp edges are the enemy of stealth. Sharp edges causes radar waves to scatter in all directions. Radar can even travel along the length of a surface in the form of a travelling wave and then scatter upon reaching the trailing edge.
Okay.
The strength of that return signal can be reduced with a few clever techniques. The strength of the signal will depend on the length of the edge. So, the first technique is to reduce the edge length with serration. You can see this technique implemented very clearly on the trailing edge of the V2. However, it's less obvious where it's used for the F-35, until you start looking at all the access hatches hidden around the aircraft. Every single unavoidable surface gap on the aircraft has a serrated edge. This hatch opens to reveal a telescoping ladder to allow pilots to climb in and out of the aircraft. These open to reveal the landing gear. These are the internal weapons bay, essential for keeping the radar reflecting missiles hidden from view, and these smaller hatches are flare dispenser doors. Flares are effective decoys for heat-seeking missiles, but they do nothing to prevent radar-guided missiles. In the face of radar-guided missile proliferation and continued growing sophistication in the technology, a new decoy system was developed. This new technology is released from this panel. When needed, this access door opens and a transmitter begins to reel out to a safe distance behind the plane. It has 3 levels of countermeasures to protect the F-35 from attack. First, it actively jams missiles while they attempt to lock onto their target, by emitting jamming signals which the onboard computer computes and delivers to the emitter through the fiber optic tow line. If the radar manages to obtain a lock, it then begins to attempt to break the lock, disrupting the tracking algorithms guiding the missile towards its target. Finally, if all is lost and the missile is bearing down on the aircraft, the emitter begins to simulate the aircraft's radar signature, drawing the missile toward it as a decoy. These serrated hatches hide critical components of the F-35.
That's mental.
But more can be done to reduce edge scattering in these locations. You may notice that the colour around these edges is different to the rest of the plane. This is because the edges are treated with a special radar scattering tape. In the same way travelling waves scatter when they meet an edge discontinuity, they will scatter when travelling over a change in conductivity. The F-35 uses this to its advantage to scatter waves over a longer distance, reducing the return signal by spreading it out. The tape has a conductivity gradient, gradually decreasing its electrical conductivity, causing radar waves to scatter at each interval, slowly decreasing the intensity of the surface wave before it reaches the edge where it would have released one large return if the tape was not present. The surface of the plane itself is also composed of a specialized radar absorbing material. In 2010, Lockheed Martin filed this patent for a carbon nanotube infused composite material that can absorb radar waves from 0.1 MHz through to 60 GHz. This is an incredibly wide range of frequencies, notably covering the frequencies Russian surface-to-air missiles like the Advanced S-400 system uses. The effect travelling surface waves have on stealth design can be seen elsewhere. You would imagine a cylinder would be a great way to scatter radar in all directions, lowering the strength of the return signal. But if a radar wave comes in tangentially to a cylinder, and the wavelength is at least 1/10 the cylinder's circumference, the wave can actually travel around the outside of the cylinder and travel straight back to the receiver. This is likely why the F-35 features a sharp edge breaking up the circular nose cone. Where the F-16 has a nearly perfect circular nose cone, the F-35 features a ridge.
They've literally left no stone unturned on this, have they? You know, with technology advancing, such as weapon systems, then so have, you know, the equipment, the aircrafts, the vehicles, down to like the little radar extending out of the back to obviously defend itself against radar missiles. It's all the little details that they're obviously learning from in the past to not having a perfectly circular nose cone. I think it's outstanding and mind-boggling, some of it, that this is how much how in depth they've been going with this F-35 and why it is pretty much ranked as the best fighter jet in the world.
The largest hatch on the plane is strangely not serrated, and this is for good reason. This hatch hides the powerful lift fan within. The airflow in and out of this lift fan needs careful consideration. The lift fan is essentially a tiny helicopter, capable of generating 85 kilonewtons of vertical thrust, and in doing so creates a low pressure zone above the plane, violently sucking air into the aircraft at a 90-degree angle. This air has to travel over the hood to reach the inlet, and thus the hood needs to allow air to smoothly pass over it without creating too much turbulent flow, which would lower the performance of the lift fan. This is why the inlet door is not serrated, as the sharp edges would cause distortions in the flow. This hood alone went through several design iterations to optimize the airflow flowing over it. The demonstration X-35 aircraft had 2 doors opening towards the side of the aircraft, but this was changed for the final aircraft in favor of a rear hinged door. This helps funnel air into the engine and improves pressure recovery on short takeoffs where the F-35B does not take off vertically, instead using the lift fan and directional thrust of the rear nozzle to take off on extremely short runways. The way this aircraft transforms to perform vertical landing and short takeoffs is astounding.
Look how short that is.
The transformer we have ever created.
I didn't know the F-35 could do that. I did not know the F-35B could do that. I knew they were getting more capable of being able to take off from shorter runways. Obviously, you've got the bigger aircraft carriers. But I did not know that the hatch opened up and then it had an air inlet to then create thrust and then help it take off. I think that's brilliant. I actually really did not know that.
When the time comes, a clutch linking the extended drive shaft of the F-35's engine begins to transfer 29,000 horsepower to the bevel gear of the lift fan, spinning the contra-rotating lift fan blades. Simultaneously, gears begin to rotate in the rear exhaust nozzle. The mechanics of this nozzle are another wonder to behold. Called the 3-bearing swivel nozzle, it is composed of 3 airtight segments cut at angles relative to one another. We can change the shape of the nozzle by rotating these angled pieces separately. These 3 pieces rotate together to smoothly transition thrust downwards, but it's easier to understand how it works by seeing what happens when we rotate segments individually. Rotating the central piece can take the nozzle from 0 degrees down to 45 degrees. This position is used for short takeoffs, splitting the engine's power between thrust and lift. This mode is as impressive as the vertical takeoffs, allowing the plane to operate from shorter amphibious assault ships like the USS Mackinac Island, a ship just 258 meters long. Its minimum takeoff distance decreases even further with the aid of a ski jump, a ramp that has been added to smaller amphibious assault ships. Watching the F-35 take off over such short distances is incredible. In this clip, we can see the rear nozzle quickly adjusting its angle of thrust in sync with the rear elevators to adjust the pitch of the plane to ensure a safe takeoff.
I think it's mad that they've managed to create that can move with the elevators at the same time to enable it. It's not the fact it has to be moved when it's sort of stationary or anything. It can be altered at all times so the aircraft can change what it needs to do within an instant.
A vertical landing, the final nozzle segment can rotate to provide the full 90-degree turn. The first nozzle segment can rotate to move the nozzle from side to side, but here it's needed to ensure that thrust doesn't move sideways as the nozzle transitions. As we saw, when we rotate the segments individually, they move in an arc that would cause the F-35 to spin out of control.
Look at that.
This mechanism also allows the F-35 to smoothly transition from cruise to vertical flight and from vertical flight to cruise when needed. There are additional control mechanisms to ensure this precarious balancing act does not go wrong. Bleed air from the main engine bypass is siphoned to 2 roll nozzles located on each wing, providing thrust far away from the plane's center of pressure to control roll. There are also guide vanes located underneath the lift fan. These can adjust the outlet area to adjust the performance of the lift fan, but can also control the thrust of the lift fan from 5 degrees forward to 42 degrees backwards. With computer-assisted control of these control mechanisms, the F-35 is remarkably stable compared to its predecessor, the AV-8B Harrier, allowing the single engine of the F-35 to hover on 2 columns of air. To do this, the F-35's engine, the F-135, developed from the F-119 engine of the F-22 Raptor, had to be incredibly powerful. The F-22 Raptor is a twin-engined fighter, giving it plenty of excess power to pull off incredible maneuvers. The F-35 only has one engine, and needs to squeeze out all the power it can get to perform a vertical landing. Where the F-22's engine can generate 156 kilonewtons of thrust, the F-35's can generate 191. The F-35's engine has a much larger fan and bypass ducting, giving it twice the bypass ratio of its F-22 counterpart, providing the F-35 with a more efficient engine for cruise, but also a higher mass flow rate for higher thrust. However,
so they've managed to engineer a single engine better than a twin engine.
This does come with some drawbacks. Air that travels around the engine core completely avoids the combustion chamber, and thus misses out on the acceleration generated there, reducing the exhaust velocity. This reduces the top speed of the plane. The max speed of the F-35 is 1.6 Mach, and while it's the first plane capable of vertical flight and supersonic flight, the F-22 can fly at 2.2 Mach. The F-35 was optimized for loiter time, not speed. However, all that extra weight needed for vertical takeoff seriously hampers that ideology. The lift fan module weighs 1.2 tons, weight that does nothing in normal flight and requires more fuel to carry. And to make matters worse, that space is used for internal fuel tanks for its variants. Making the lift fan as light as possible was pertinent to making the F-35B viable in the battlefield. The fact it only weighs 1.2 tons is astounding. It
It's still heavy though.
Counter-rotating titanium blisks. Blisk meaning the blades and disc are all one single piece, instead of the traditional alternative of creating a disc and attaching blades through dovetail connections. This improves efficiency and eliminates a potential site of failure in the connection. This is an astounding feat of manufacturing, and the first stage fan takes it even further. The first stage blades are hollow to save weight. Where the F-35B truly comes into its own, however, is in its modern suite of sensors and computers, all feeding into this. The heads-up display incorporated into the pilot's helmet.
I love this, this is brilliant.
Heads-up displays, like those of the F-16, are incorporated into a panel in the cockpit, a panel which the pilot can't see while scanning their environment. Situational awareness is everything in the heat of combat, and this helmet does it.
That's so true, and I've said it in so many previous videos. Situational awareness is key. The more situational awareness you've got, the better the outcome. Whether that's being a soldier, fighter pilot, driving a vehicle, being in the Navy, no matter what's going on, if you're going into a situation and you've got as much awareness as possible, especially being in a fighter jet, being a pilot, there's so much going on. Whether you're out on a reconnaissance mission, whether you're doing air-to-ground attacks, whether you're doing air-to-air, or whether, I don't know, just for say, you're talking to ground troops, you still need to know what's going on. You need to know where friendlies are, you need to know what's going on with enemy positions, you need to know where you are going on the map, where you are, currently, you need to know how fast you're going, what's going on with the aircraft, what's the fuel like, what's your speed. This is all situational awareness, and the better understanding you've got of that, the easier it is to have all that information, the better. So having it in the helmet is going to give them that. Bearing in mind they most probably got 2 or 3 nets going on in their heads, they've got to understand that, they've got to pass messages through. So like they said in previous variants where it was on the display on the screen, when you're looking around seeing what's going on, you're then losing situational awareness at the front. But if you've got that in a head-up display and you're looking around and you're gathering more situational awareness going on that's around you, you've still got that head-up display, so you still know that information, which is going to make your life easier.
Everything it can to keep the pilot informed, even giving them X-ray vision and
X-ray vision.
Information from a suite of sensors around the plane feed into a central computer, where it is processed and displayed through a projector inside the helmet.
I'd love to see this. How insane.
The faceted box underneath the aircraft is a suite of sensors, but those are not your typical windows. These windows are made from a notoriously expensive gemstone, sapphire. one of the few materials that is both hard and durable, but also transparent to a broad range of electromagnetic wavelengths, from ultraviolet to infrared. However, the radar antenna hidden inside the nose of the F-35 is the most important part of this electronic system. This is a scanned array radar that works very differently to traditional mechanical radar. Phased array antennas have hundreds of tiny antennas. We can see metal plates set in rows in the F-35 phased array antenna. The metal plates have slots cut into them, and each and every one of these slots is an antenna, 1,600 in total.
It's a lot of
This
antennas.
allows the phased array antenna to steer its radar using constructive and destructive interference. If two antennae release two radar waves at the exact same time with their peaks and troughs lined up, it will result in constructive interference, increasing the amplitude of the radio wave. However, if the radio waves are set 180 degrees out of phase, matching the peaks to troughs, it will result in complete destructive interference, cancelling
interesting.
out the wave completely. This is how noise-cancelling earphones work. They listen to the background noise and then release a cancelling sound wave to create silence. Phased array antennae use this phenomenon to steer the radio waves, preventing the radar from becoming a giant beacon, leading enemies straight to it. Traditional phased array antennas are passive, meaning every antenna in the array is driven by a single transmitter and receiver. This would mean it can only point in one direction, and if it encountered two enemy planes flying side by side and they split up, the passive phased array antenna would no longer be able to track both of them. However, the F-35's phased array antenna is an active phased array, meaning each and every one of these antennae is an individually driven transmitter and receiver, meaning the F-35 can track multiple targets at once with zero moving parts.
So it's got 1,600 individual antennas, so it can understand exactly what's going on. It can pinpoint different aircrafts. Oh, that's pretty good. That's really good. The technology on this is just insane.
The nose cones hiding these antennae need to be transparent to radar waves, and are usually made from glass fiber composites as a result. This transparency causes issues for the plane's radar return signature, as an antenna like this will reflect signals. This was a much bigger issue for mechanical radar dishes that needed to point at the enemy to keep track of them. The phased array can point towards multiple targets while staying in a single position, and this is why it is pointed skywards, to bounce incoming radar to space. The phased array antenna also acts as the plane's communication antenna, and this is critical to the F-35's battle doctrine. The F-35 excels in battle because of its networking abilities, relaying information between its squadron. This is a huge amount of data to transfer between aircraft and allies on the surface, and requires a high data transfer speed. However, communication comes with one glaring problem. It announces your presence to anyone listening.
Yep.
It is vital that stealth planes can communicate with each other securely, and the active phased array antenna facilitates this. The F-35 uses the latest data link system, MADL, improving on the experiences learned with the F-22, allowing the F-35 to quickly share data securely from individual F-35s and ground-based systems.
So they can send each other data without having to do it over voice. This is the way a lot of militaries go in. The British Army are trying to send data now. It's more accurate, it's faster, there's less chance of you getting things wrong, and it can be more secure. So yes, they can talk to each other by voice, but what I'm getting from this is that they can send data, share data with each other so everyone understands. So the commander within that, what they called team, can share data so everyone understands what's going on without having to send it over voice, which can be unsecure and obviously alert of your presence.
This information is then sorted by the computer and presented to the pilot in their heads-up display in front of their eyes, giving them unparalleled situational awareness.
Once again, back to the situational awareness.
To communicate with their wing mates if there is an adversary underneath them.
That's mad. That's really good that you can do all that without communicating over voice. As we know, voice alerts of your presence, and it's not as secure as if you're sending it by data.
Planes communicate and feed that data right into the helmet, allowing the pilot to look underneath the plane and see the location of the adversary themselves. This is the true strength of the F-35B. It is a networked hive mind stealth fighter, capable of taking off from a ship a fraction of the size of an aircraft carrier, and returning while hovering in the sky like a helicopter. It's one of the most remarkable pieces of military technology ever created. The F-35 has borrowed many lessons learned from planes like the F-117 Nighthawk and B-2, planes that we have not made documentaries about yet, but our friends over at Mustard have. Their B-2 documentary...
Absolutely brilliant. Way above me, some of that, but I find it very, very interesting to learn, and someone recommended this video to me. So thank you for recommending it. If anyone else wants to recommend anything else, please, I will add it to my list. I've got lots of recommendations and I do try and get through them as best as possible. Like I said, a lot of information, may have to watch that again, but it really gives you into a massive insight into the actual engineering, you know, the research and development that's gone into the F-35B, the pros and cons of previous planes. So they've learned from the mistakes they've made, but then also the things that have worked. So obviously with the tail fin, you don't want a 90-degree angle, so they've gone for the 2 at a slight angle, like you saw in the B-2 and the 117, and even the small private jet. There's just so much information in there. It's absolutely insane. I think just the technology of sort of where do you go from here. I'm really, really interested to know where do we go from here, because you've got a stealth fighter that, okay, like we said, isn't invisible, but can really minimize the radar, can delay the notification of you being there. It can possibly, looks like with its extendable radar, have a defense against radar missiles. It's obviously got the flares for heat-seeking missiles. It's got the patterned in tape, all the angles. So sort of where do you go from here? It's got a head-up display in the helmet. It's got night vision. It's got X-ray. Yeah, I'm just really interested to go. Where do fighter jets, like stealth fighters, go from here? But I really, really thank you for sending this video over. I really, really enjoyed it. I think, yeah, it's just mind-boggling just where we're at. I didn't know half of those things about the F-35, the vertical takeoff, the short runway takeoff, the head-up display I sort of knew of. I didn't know about the X-ray. I think that's brilliant. I think the way it can transfer data, it's got 1,600 antennas, and it's able to transfer data between other pilots within their team, is absolutely brilliant. Like I said, the British Army are looking to go to data because it's a lot more accurate. It can be secure, it can be faster. Obviously with voice there could be miscommunication. You know, they can sort of break into it, they can hack it, and then obviously on the other end you might misinterpret what they said. With data, it gets written and sent, whether that's on a screen on a laptop or you're in the F-35B and it comes up on your head-up display. It's there, then you see it, so you can't sort of misinterpret. You can't hear it incorrectly when it's said over voice. Yeah, I think I can see why now, looking at this, why they cost so much to make. Most of it has got to go into the research and developing and trialing different ways to obviously break against radar. That's obviously the main thing with this, is with it being such a stealth fighter, so much has gone into every little thing. No stone has been unturned to minimize its radar presence as much as possible, to minimize it rebounding back at a right angle or with a stronger strength. Yeah, hopefully you enjoyed the video. Thanks for watching, and I'll see you soon.